Swayam Prabha. Digital India. Educated India.
In this lecture, I will describe a technique called logistic regression. Logistics regression is a classification technique which basically develops linear boundary regions based on certain probability interpretations. While in general we develop linear decision boundaries, this technique can also be extended to develop nonlinear boundaries using what is called polynomial logistic regression. For problems where we are going to develop linear boundaries, the solution still results in a nonlinear optimization problem for parameter estimation, as we will see in this lecture. So the goal of this technique is, given a new data point, I would like to predict the class from which this data point could have originated. So in that sense, this is a classification technique that is used in a wide variety of problems, and it is surprisingly effective for a large class of problems. Just to recap things that we have seen before, we have talked about binary classification problem before. Just to make sure that we recall some of the things that we have talked about before, we said classification is the task of identifying what category a new data point or an observation belongs to. There could be many categories to which the data could belong, but when the number of categories is 2, it is what we call as the binary classification problem. We can also think of binary classification problems as simple yes or no problems, where you either say something belongs to a particular category or no, it does not belong to that category. Now, whenever we talk about classification problems, we have described this before. We say a data is represented by many attributes x1 to xn. We can also call these as input features, as shown in the slide, and these input features could be quantitative or qualitative. Now, quantitative features can be used as they are. However, if we are going to use a quantitative technique, but we want to use input features which are qualitative, then we should have some way of converting these qualitative features into quantitative values. One simple example is if I have a binary input like a yes or no for a feature. So what do we mean by this? So I could have yes, let's say 0.1, 0.3, and then another data point could be no, 0.05, -2, and so on. So you notice that these are quantitative numbers while these are qualitative features. Now you could convert this all into quantitative features by coding yes as 1 and no as 0. So then those also become number. This is a very crude way of doing this. There might be much better ways of coding qualitative features into quantitative features and so on. You also have to remember that there are some data analytics approach that can directly handle these qualitative features without a need to convert them into numbers and so on. So you should keep in mind that that is also possible. Now that we have these features, we go back to our pictorial understanding of these things. Just for the sake of illustration, let's take this example where we have this two-dimensional data. So here we would say x is x1, x2, two variables. Let's say x1 is here, x2 is here. So it's organized into data like this. Now let's assume that all the circular data belong to one category and all the star data belong to another category. Notice that circle data would have certain x1 and certain x2, and similarly star data would have certain x1 and certain x2. So, in other words, all values of x1 and x2 such that the data is here belongs to one class, and such that the data is here belongs to another class. Now, if we were able to come up with hyperplane such as the one that is shown here, we learned from our linear algebra module that to one side of this hyperplane is a half space, this side is a half space, and depending on the way the normal is defined, you would have a positive value and a negative value to each side of the hyperplane. So, this is something that we had dealt with in detail in one of the linear algebra classes. So, if you were to do this classification problem, then what you could say is if I get a data point somewhere here, I could say it belongs to whatever this class is here. So, let us call this, for example, we could call this class 0, we could call this class 1, and we would say whenever a data point falls to this side of the line, then it is class 0. And if a data point falls to this side of the line, we will say it is class 1 and so on. However, notice that any data point, so whether it falls here or it falls here, we are going to say class 0, but intuitively you know that if this is really a true separation of these classes, then this is for sure going to belong to class 0, but as I go closer and closer to this line, there is this uncertainty about whether it belongs to this class or this class, because data is inherently noisy. So, I could have a data point which is true value here, however, because of noise it could slip to the other side and so on. So, as I come closer and closer to this, then the probability or the confidence with which I can say it belongs to a particular class can intuitively come down. So, simply saying yes, this data point and this data point belongs to class 0 is one answer, but that is pretty crude. So, the question that this logistics regression answers is, can we do something better using probabilities? So, I would like to say that the probability that this belongs to class 1 is much higher than this because it is far away from the decision boundary. So, how do we do this is the question that logistics regression addresses. So, as I mentioned before, the probability of something being from a class, if we can answer that question, that is better than just saying yes or no answers, right. So, one could say yes, this belongs to a class. A better nuanced answer could be that yes, it belongs to a class, but with a certain probability. As the probability is higher, then you feel more confident about assigning that class to that data. On the other hand, if we model through probabilities, we do not want to lose binary answer like yes or no also. So, if I have probabilities for something, I can easily convert them to yes or no answers through some thresholding, which we will see in the logistics regression methodology when we describe that. So, while we do not lose the ability to categorically say if a data belongs to a particular class or not by modeling this probability, on the other hand, we get a benefit of getting a nuanced answer instead of just saying yes or no. So, the question then is, how does one model these probabilities? So, let us go back and look at the picture that we had before. Let us say this is x1 and x2. Remember that this hyperplane would typically have this form. Here the solution is written in the vector form. If I want to expand it in terms of x1 and x2, what I could do is I could write this as beta naught plus beta 11 x1 plus beta 12 x2. So, this could be the equation of this line in this two-dimensional space. Now, one idea might be just to say this itself is a probability, and then let us see what happens. The difficulty with this is this p of x is not bounded because it is just a linear function, whereas you know that the probability has to be bounded between 0 and 1. So, we have to find some function which is bounded between 0 and 1. The reason why we are still talking about this linear function is because this is the decision boundary. So, what we are trying to do here is really instead of just looking at this decision boundary and then saying yes and no, plus and minus, what we are trying to do is we are trying to use this equation itself to come up with some probabilistic interpretation. That is the reason why we are still sticking to this equation and trying to see if we can model probabilities as a function of this equation, which is the hyperplane. So, you could think of something slightly different and then say, look, instead of saying p of x is this, let me say log of p of x is beta naught plus beta 1 x. In this case, you will notice that it is bounded only on one side. In other words, if I write log of p of x is beta naught plus beta 1 x, I will ensure that p of x never becomes negative. However, on the positive side, p of x can go to infinity. That again is a problem because we need to bound p of x between 0 and 1. So, this is an important thing to remember. So, it only bounds this on one side. So, is there something more sophisticated we can do? The next idea is to write p of x as what is called a sigmoidal function. The sigmoidal function has relevance in many areas. So, this is a function that is used in neural networks and other very interesting applications. So, the sigmoid has an interesting form which is shown here. Now, let us look at this form right here. I want you to notice two things. Number one is still we are trying to stick this hyperplane equation into the probability expression because that is the decision surface. Remember, intuitively somehow we are trying to convert that hyperplane into a probability interpretation. So, that is the reason why we are still sticking to this beta naught plus beta 1 x. Now, let us look at this equation and then see what happens. So, if you take this argument beta naught plus beta 1 x, so that argument depending on the value of x you take could go all the way from minus infinity to infinity, right. So, just take a single variable case. If I write let us say beta naught plus beta 1, just one variable x, not a vector. Now, if beta 1 is positive, if you take x to be a very large value, this number will become very large. If beta 1 is negative, if you take x to a very large value in the positive side, this number will become minus infinity, and similarly if beta 1 takes the other values, you can correspondingly choose x to be positive or negative and then make this unbounded between minus infinity to infinity. So, we will see what happens to this function when beta naught plus beta 1 x is minus infinity. You would get this to be e power minus infinity plus divided by 1 plus e power minus infinity, or you can just think of this as minus very large number. So, in that case the numerator will become 0 and the denominator will become 1 plus 0. So, on the lower side this expression will be bounded by 0. Now, if you take beta naught plus beta 1 x to be a very large positive number, then the numerator will be a very large positive number and the denominator will be 1 plus that very large positive number. So, this will be bounded by 1 on the upper side. So, now from the equation for the hyperplane, we have been able to come up with a definition of a probability which makes sense, which is bounded between 0 and 1. So, it is an important idea to remember. By doing this, what we are doing is the following. If we were not using this probability, all that we will do is we will look at this equation and whenever a new point comes in, we will evaluate this beta naught plus beta 1 x, and then based on whether it is positive or negative, we are going to say yes or no, right. Now, what has happened is instead of that, this number is put back into this expression, and depending on what value you get a probabilistic interpretation. That is the beauty of this idea here. You can rearrange this in this form and then say log of px by 1 minus px is beta naught plus beta 1x. The reason why I show you this form is because the left hand side could be interpreted as log of odds ratio, which is an idea that is used in several places. So, that is the connection here. Now, we have these probabilities, and remember if we were to write this hyperplane equation as the way we wrote in the last few slides, beta naught plus beta 1 1 x1 plus beta 1 2 x2, the job of identifying a classifier as far as we are concerned is done when we identify values for the parameters beta naught, beta 1 1 and beta 1 2. So, we still have to figure out what are the values for this. Once we have a value for this, anytime I get a new point, I simply put it into the p of x equation that we saw in the last slide and then get a probability, right. So, this still needs to be identified. And obviously, if we are looking at a classification problem where I have this on this side and stars on this side, I want to identify these beta naught, beta 1, beta 1 1 and beta 1 2 such a way that this classification problem is solved. So, I need to have some objective for identifying these values, right. Remember in the optimization lectures I told you that that all machine learning techniques can be interpreted in some sense as an optimization problem. So, here again we come back to the same thing and then we say, look, we want to identify this hyperplane, but I need to have some objective function that I can use to identify these values. So, these beta naught, beta 1 1 and beta 1 2 will become the decision variables, but I still need an objective function. And as we discussed before when we were talking about the optimization techniques, the objective function has to reflect what we want to do with this problem. So, here is an objective function, looks little complicated, but I will explain this as we go along. So, I said in the optimization lectures we could look at maximizing or minimizing. In this case, what we are going to say is I want to find values for beta naught, beta 1 1 and beta 1 2 such that this objective is maximized. So, take a minute to look at this objective and then see why someone might want to do something like this. So, when I look at this objective function, let us say I again draw this and then let us say I have these points on one side and the other points on the other side. So, let us call this class 0 and let us call this class 1. So, what I would like to do is I want to convert this decision function into probabilities. So, the way I am going to think about this is when I am on this line, I should have the probability being equal to 0.5, which basically says that if I am on the line, I cannot make a choice between class 1 and class 2 because the probability is exactly 0.5. So, I cannot say anything about it. Now, what I would like to do is you can interpret it in many ways. One thing would be to say as I go away from this line in this direction, I want the probability of the data belonging to class 1 to keep decreasing. The minute that the probability that the data belongs to class 1 keeps decreasing, that automatically means since there are only two classes and this is a binary classification problem, the probability that the data belongs to class 0 keeps increasing. Okay. So, if you think of this interpretation where as I go from here, so here the probability that the data point belongs to class 1 let us say is 0.5, then basically it could either belong to class 1 or class 0. And if it is such that the probability keeps decreasing here of the data point belonging to class 1, then it has to belong to class 0. So, that is a basic idea. So, in other words, we could say the probability function that we defined before should be such that whenever a data point belongs to class 0 and I put that into that probability expression, I want a small probability. So, you might interpret that probability as the probability that the data belongs to class 1, for example, and whenever I take a data point from this side and put it into that probability function, then I want the probability to be very high, because I want that is the probability that the data belongs to class 1. So, that is a basic idea. So, in other words, we can paraphrase this and then say, for any data point on this side belonging to class 0, we want to minimize p of x when x is substituted into that probability function, and for any point on this side, when we substitute these data points into the probability function, we want to maximize that probability. So, if you look at this here, what this says is, if this data point belongs to class 0, then yi is 0. So, whenever a data point belongs to class 0, anything to the power 0 is 1. So, this will vanish. So, in the product there will be functions of this form, which will be 1 minus p of xi, and because yi is 0, this will become 1. So, this will become something to the power 0 1. So, this term will vanish, and the only thing that will remain is 1 minus p of xi. So, if we try to maximize 1 minus p of xi, then that is equivalent to minimizing p of xi. So, for all the points that belong to class 0, we are minimizing p of xi. Now, let us look at the other case of a data point belonging to class 1, in which case yi is 1. So, 1 minus 1 0. So, this term will be something to the power 0, which will become 1. So, it kind of drop out. So, the only thing that will remain is p of xi. Now, yi is 1. So, power 1, you will be just left with p of xi. And since this data belongs to class 1, I want this probability to be very large. So, when I maximize this, it will be a large number. So, you have to think carefully about this equation. There are many things going on here. Number one, that this is a multiplication of the probabilities for each of the data points. So, this includes data points from class 0 and class 1. The other thing that you should remember is, let us say I have a product of several numbers. If I am guaranteed that every number is positive, right, then the product will be maximized when each of these individual numbers are maximized. So, that is a principle that is also operating here. That is why we do this product of all the probabilities. However, if a data point belongs to class 1, I want probability to be high. So, the individual term is just written as p of xi. So, this is high for class 1. When a data point belongs to class 0, I still want this number to be high. That means this number will be small. So, it automatically takes care of this as far as class 0 and class 1 are concerned. So, while this looks little complicated, this is written in this way because it is easier to write this as one expression. Now, let us take a simple example to see how this will look. Let us say I have class 0, I have two data points x1 and x2, and class 1 I have two data points x3 and x4. So, this objective function, when it is written out, would look something like this. So, when we take, let us say, these points belonging to class 0, then I said the only thing that will be remaining is here. So, this will be 1 minus p of x1. For the second data point, it will be 1 minus p of x2. Then for the third data point, it will be p of x3, and for the fourth data point, it will be p of x4. So, this would be the expression from here. So, now when we maximize this, then since p of x's are bounded between 0 and 1, this is a positive number, this is a positive number, positive number, positive number, and if the product has to be maximized, then each number has to be individually maximized. That means this has to be maximized. So, it will go closer and closer to 1. The closer to 1, it is better. So, you notice that x4 would be optimized to belong in class 1. Similarly, x3 would be optimized to belong in class 1. And when you come to these two numbers, you would see that this would be a large number if p of x1 is a small number. So, p of x1 basically means that x1 is optimized to be in class 0 and similarly x2 is optimized to be in class 0. So, this is an important idea that you have to understand in terms of how this objective function is generated. Now, one simple trick you can do is take that objective function and take a log of that and then maximize it. So, if I am maximizing a positive number x, then that is equivalent to maximizing log of x also. So, whenever this is maximized, that will also be maximized. The reason why you do this, it makes the product into sum, makes it looks simple. So, remember from our optimization lectures we said okay, we are going to maximize this objective. So, we always write this objective in terms of decision variables, and the decision variables in this case are beta naught, beta 11 and beta 12 as we described before. So, what happens is each of these probability expressions, if you recall from your previous slides, will have these 3 variables, and xi are the points that are already given. So, you simply substitute them into this expression. So, this whole expression would become a function of beta naught, beta 11 and beta 12, right. Now, we have come back to our familiar optimization territory, where we have this function which is a function of these decision variables. This needs to be maximized, and this is an unconstrained maximization problem because we are not putting any constraints or beta naught, beta 1 and beta 2. So, they can take any value that we want, and also the fact that the way the probability is defined, this would also become a nonlinear function. So, basically we have a nonlinear optimization problem in several decision variables, and you could use any nonlinear optimization technique to solve this problem. And when you solve this problem, what you get is basically the hyperplane. So, in this case it is a 2-dimensional problem. So, we have 3 parameters. Now, if there is an n dimensional problem, if you have let us say n variables, so I will have something like beta naught plus beta 11 x1 plus beta 12 x2 and so on plus beta 1n xn. This will be an n plus 1 variable problem. There are n plus 1 decision variables. These n plus 1 decision variables will be identified through this optimization solution, and for any new data point, once we put that data point into the p of x function, that sigmoidal function that we have described, then you would get the probability that it belongs to class 0 or class 1. So, this is the basic idea of logistic regression. In the next lecture, I will take a very simple example with several data points to show you how this works in practice, and I will also introduce a notion of regularization which would help in avoiding overfitting when we do logistics regression. I will explain what overfitting means in the next lecture also. With that, you will have a theoretical understanding of how logistics regression works, and in a subsequent lecture Dr. Hemant Kumar would illustrate how to use this technique in R on a case study problem. So, that will give you the practical experience of how to use logistics regression and how to make sense out of the results that you get from using logistics regression on an example problem. Thank you, and I will see you in the next lecture.